Okay, let's look at our final example. So some harder pulley questions that look something like this. This is quite a common exam favorite, this one. So very good one to be good at, okay? Two particles A and B have masses of 0.4 kilograms and 0.8 kilograms respectively. Okay, well, they're masses, so I might need to use them for F equals MA. They have weights as well. I might need to use them for their weights. They're connected by a light inextensible string. Remember, that means that when we find out the acceleration, that's it. That's the acceleration for this situation, whether it's block A or block B. Okay. Particle A lies on a rough horizontal table 4.5 meters from the pulley. Now, why would they tell me about meters? Maybe it's got something to do with the Suvat equation later on. Rough table, well, I'm expecting there's probably going to be something holding me back. A smooth fixed pulley, okay. At the end of the table, the string passes over the pulley and hangs freely. Yeah. With the string taut 0.5 meters above the ground. So that sounds like it's 0.5. Again, it sounds like that's got something to do with the Suvat later on. The frictional force, this must be the rough table. So there's a frictional force acting on A, holding it back, is 0.08 G. The system is released from rest. Well, we know to watch out for that one there. U is equal to 0, maybe. Let's have a go. So, as always, we start by drawing all of the forces acting on these particles and any other information. So, just check that you're happy with all of these forces here. So, a weight, 0.4 G, it's reaction. A weight, 0.8 G, no reaction. It's not on a table. It's being supported by a string, so the tension in the string must be pulling it up. The tension is the same tension that also pulls block A towards the pulley. And then we've also got some forces on the pulley again. So that might be like a part C question, part D. Maybe it might not be involved at all. And there's the friction. Okay. Which way is it moving if it's released from rest? Well, it's going like this, isn't it? A is going over here. B is going down. I think we've got some arrows for those. I'm not sure what's going on with that one there, so let's ignore that. But it's accelerating across to the pulley and down. So as before with the pulleys, what we do is we make equations about each of them. So an equation, a force, resultant force for A, resultant force for B, and then you can probably guess already F equals ma is what we're going to do to find this acceleration here. Now, there's lots and lots of forces on A, but I'm not actually interested in all of them. The R in the 0.4 G, that just tells me that the thing has a weight and that that weight is supported, okay? So that's not really what this question is about. This question is about moving towards the pulley. So I'm more interested in the horizontal forces for the block that's on the table. So T is the leading force and is held back by 0.08 G. There we go. Its mass is 0.4, not its weight. Its mass is 0.4, and the A is unknown. We want to work that out. Let's do the same now for B. The leading force is 0.8 G. It's held back by T, and that's it. 0.8 G minus T. It had a mass of 0.8, and there's A. Now, you're probably at the point where you feel like you know what to do with these here. So even though the questions can get really, really, really hard, there's no excuse for not trying to get all of the forces labeled. Think about the resultant force. F equals ma is the way many of these questions will go, okay? And trying to solve it simultaneously. Even if you cannot master everything, there's lots of marks that can be earned there, which are not too bad. We add them together again, okay? We add these together. That will get rid of the t's if you add them together. And you'll get 0.7 G equals 1.2a. Well, rearrange 0.6 equals G, 0.6 G equals A. That's the final answer because you know what G is, remember. You know it's 9.8. So 0.6 G equals A. It's the A for this bit here. It's the A for this bit here. It's the acceleration for this system. There we go. Acceleration equals 0.6 G. The velocity at which B hits the ground. Now, I would be very rich if I had £1 for every time somebody said this to me. The velocity equals 0. Well, there's a couple of things wrong with that. So first of all, why would that be a question? It's not going to be like a 3 or 4 mark question if it were just that. There must be more going on. And the other thing that's wrong with it is the velocity at which you hit the ground is different to the velocity after you hit the ground. It might be 0 after it hits the ground, but the way we use v means like the moment just before, like the instant just before. So if it helps, try to think of the block being like just off the ground, okay? And then it will sort of dismiss that idea for v equals 0. So we're talking about block B. We're talking about V. I can see an S there, which is 0.5. I know that the acceleration is 0.6 g. And I know that it was released from rest. So we've got a SUVAT situation here. Okay. You don't need t, so this is the equation to use. And if you substitute in your values, you get your answer here, 2.42. So look, it's not 0, is it? It's being released. It's bringing some velocity to the question just as it's about to hit the ground. So when it hits the ground, that means when it's just about to hit the ground. Okay? Now, these ones are not so bad. Here's the tricky one. So here's the final one. This is the tricky one. So what distance does it travel before it comes to rest? What distance does A travel, this block here? Well, you know that it's inextensible. So if you move this by 0.5, you know that it's going to move by 0.5. So is that the answer? No, it's a bit more complicated than that. But 0.5 is part of it. That's definitely part of the answer. So particle A will travel 0.5 by the time it hits the floor. Yep. So it's at least 0.5. However, when B hits the ground, what's going to happen to this string here, this inextensible string? Well, it's going to become slack. It's not taut. And when it's not taut, it doesn't have any tension. So the string sort of, when B hits the ground, the string in effect sort of disappears. Well, it doesn't disappear, it just doesn't do anything. So on our force diagram, it's gone. Well, whenever we change the forces because a cable snaps or it goes slack or something like that, we have to do a force diagram again. And what are the forces horizontally acting on A? Well, it's just one. It's minus 0.08 g. That will become your new resultant force. I've done minus because I've kept the direction the same throughout the question. And this will be equal to ma. So what will happen is you will get a new acceleration. And think about this logically. If it went like this and then the string is sort of gone, what's going to happen to A? It's got this speed, but then suddenly the force pulling it forwards is gone. It's going to just sort of slow down and it's going to stop. It's going to stop on this table here. So we do F equals ma again, but t is now 0, so it's gone because the line is slack. This will give you an acceleration, and that acceleration is negative. That means the block is going to slow down, it's going to stop. So for the second part of the question, after the 0.5, that's kind of the first part of the question. For the second part, when this is all gone here, you will have the speed from before, because that's what it was traveling at as it moved like that. That's what it was traveling at. But because the tension went, there's a new acceleration and it's going to stop. It's going to stop because it has some velocity to it and it's decelerating and it will stop. And then it says the total distance. So we have our 4 pieces of information. And if we do all of that, we get 1.5 meters. So that might surprise you, but if something's moving already, then it's going to keep covering distance, isn't it? Even if it's not being pulled anymore, it has some velocity to it. And that's only going to disappear over time as it decelerates. We have our 1.5, and then we need to add on our 0.5. The 0.5 is when A and B were moving together. So this is actually a 2-part question. Quite a challenging one, but hopefully by sort of thinking about it a little bit before, thinking of it as 2 steps and remembering that it's really all about the force diagrams and redrawing the force diagrams when the forces change, you should be able to make sense of that one there and pick up lots of marks for it. So pause the question here and have a go at this one on the board. This is a bit like one from the earlier video, but you should now be able to have a go at this question here. Okay, so Newton's second law, that's what N2L means. This is the equation of motion for A. This is the equation of motion for B. Find the value of K. So should be able to use those together. The pulley smooth. So the fact that the pulley smooth means there's no friction. And if there's no friction, that means the tension in both strings is the same. And then you've got, look, 1.2, you've got a time value. So you've got to solve that equation here at the bottom. So that's a topic there that you're going to have to spend a fair bit of time working on. But hopefully that helps a little bit.